or whatever as the case may be. We're very happy to continue with the next session of this conference by hearing from Shruti Paranjape, who will be telling us about mass and locality in the double copy.
All right. Hello, everyone. Thank you so much for the invitation to speak. I'm delighted to be here. So today I wanted to discuss aspects of locality and unitarity in the double copy with massive external states. So this is going to be, this talk is going to be based on a paper whose archive number is given over here, which I wrote in collaboration with Laura Johnson, who is a postdoc at ETH Zurich, and Callum Jones, who is a postdoc at UCLA. Good. So most of us here are familiar with the double copy. It can be thought of as a map on the space of theories, where you map a theory C to two theories A and B in this multiplicative way, where quite often people use the shorthand that C equals A times B. And the scope of the double copy is broad. It works for tree amplitudes and loop integrands. And whichever is your favorite three-letter acronym to think of the double copy, either KLT, BCJ, or CHY, typically the first example you come across is this one over here, where you see that Yang-Mills squares, or it double copies with itself, to gravity coupled to a dilaton and an antisymmetric two form. So in 4 dimensions, this two form is just an axion scalar. All right. So our goal in this talk will be to take that usual massless double copy formalism and extend it so that it includes massive states in as generic a fashion as possible. So this includes the possibility of having all massive states. Our next step will be to understand factorization properties, locality, and massless limits in this new formalism. The example that we will focus on primarily will be massive Yang-Mills, and we will see how or whether that double copies to massive gravity. Finally, we want to understand the broader scope of this formalism to see what other amplitudes or other theories may be double copied in this fashion. All right, so before we begin to construct a massive extension of the double copy, let's understand the massless one to begin with. So good. If you were at Henrietta's talk, you will be familiar with the KLT algebra. So this is the KLT formula over here. On this side, you have a double copy amplitude in a theory C. On the right-hand side, you have two single copies, A and B, and their amplitudes, well, actually their partial amplitudes, with respect to some color orderings, alpha and beta. And you have this object that defines a multiplication rule between these amplitudes called the KLT kernel. Good. The KLT algebra refers to this table and extensions of this table, where you can think of each of these entries on the inside of the table as the column header times the row header. Good. So as you can see, there's one special element that I've highlighted over here, and that is phi cubed. So this is the cubic bi-adjoint scalar theory, and it acts as an identity in this double copy. All right, so what is this theory? This is the Lagrangian of the theory. It consists of massless scalars that are bi-adjoint, meaning that they carry two adjoint indices in possibly two distinct groups. And as a result, you can think of the amplitudes as having some double color ordered structure, the partial amplitudes as having a double color ordered structure. Because of the cyclicity of traces, this matrix of amplitudes over here is n-1 factorial times n-1 factorial in size. Now, because the bi-adjoint scalar theory is built out of structure constants FABC, you also have the Kleist-Coif relations. And in this talk, I should say that I will be focusing on tree level, and I will only be considering this type of bi-adjoint scalar theory. One could consider other color structures, but we're going to stick with FABCs in this talk. All right, so as a result, your partial amplitudes will satisfy the Kleist-Coif relations, further reducing the number of distinct color orderings to n-2 factorial. Good. So that's our starting point, an n-2 factorial cross n-2 factorial matrix of amplitudes. In the case of massless bi-adjoint scalar theory, you have further BCJ relations that reduce the rank of this matrix to n-3 factorial. Okay, what has this got to do with the double copy? Well, if you were at Henrietta's talk, then you might be familiar with this idea that using the fact that the bi-adjoint scalar is the identity, one can simply show that it follows that the KLT kernel S beta gamma is given by the inverse of a matrix of bi-adjoint scalar amplitudes. And this matrix that you're inverting over here can be any full rank submatrix of the whole matrix of amplitudes. So when I say full rank, I mean n-3 factorial in the Massless case. All right, now because it can be any submatrix, there is a choice there of basis, and your final double copy amplitude must be independent of which basis you choose. So writing that out, you see that it produces linear relations on the single copy amplitudes given over here. So these are the BCJ relations, and for a theory to be double copyable, it has to satisfy these relations. So let's look at how we're thinking about the massless double copy. We think of it in a bi-adjoint scalar forward manner. So you start with a rank n-3 factorial matrix of bi-adjoint scalar amplitudes, take the inverse, construct a kernel, check that the single copies satisfy the BCJ relations, and use the KLT formula to smash those together to give you a local double copy. Now, the key word over here is local. And it's interesting how locality comes about, actually, even in the massless double copy. It's as if the KLT kernel and the BCJ relations conspire to give you a final double copy that is indeed local. Let's see how this works. So you have these bi-adjoint scalar amplitudes. That matrix has rank 1. So you can choose any one of these elements, and 1 over that element will give you the kernel at 4 point. And different choices will give you then the BCJ relations. And the fact that the kernel takes this particular form in every representation of it makes sure that you don't have double poles or spurious poles, and that you factorize correct. Good. All right. So now we're ready to take this massless story and make it massive, right? And as I said, the way we're thinking about this is bi-adjoint scalar forward. So the first thing we're going to do is construct a massive bi-adjoint scalar theory. We will do this in the most generic fashion possible. We will dress the external states with masses, and we will allow masses on the internal channels as well. So if you take your mathematical file and you say, you take your propagators and you make them massive, and that gives you this matrix of massive bi-adjoint scalar amplitudes. The first thing to notice here that is distinct from the massless case is that this is a full rank matrix, meaning that it has rank 2. So since it is already full rank, it is its own full rank submatrix, and inverting it gives you the KLT kernel, and the KLT kernel is given over here. So this is the inverse of that matrix I showed you over here. So there are various nice properties that we should look at over here. The first is that there are no new kinematic poles that are generated. This is again distinct from some of the representations of the massless KLT, but at the same time, it's overall a good thing that there are no bad poles that are generated at this order. The second is, due to the f function sitting out in front of this inverse, 1 over f, clearly taking n to 0 will give you a pole, it'll be not smooth. And as a result, this massive double copy doesn't smoothly reduce to the massless one. Finally, because your initial matrix was full rank, you didn't really have a choice as to which basis to choose, which means there were no BCJ relations that have to be satisfied by the single copy amplitudes, meaning that any theory can be double copied within this formalism, which already should make you suspicious of this formalism. So in case you're more familiar with the color kinematics of BCJ double copy, this last statement over here is the same as saying that one can always find unique color kinematic numerators no matter what theory you're given, as long as the denominators in your color kinematic representation have been given generic masses. Good. So this is where we're at with our formalism so far. We constructed the massive bi-adjoint scalar amplitudes. We calculated the rank, and we took a full rank submatrix to make a kernel, and then we put that together to construct a double copy. And for generic masses, we found that the rank is actually, it's a full rank matrix, and so there are no BCJ relations. Remember that the BCJ relations and the kernel were what conspired to give you local double copies in the massless case. So in this case, how does one ensure that the double copy is local? Again, in color kinematic language, when are the unique color kinematic enumerators local? All right. So there are really two aspects of locality when it comes to tree amplitudes. The first is factorization. So tree level amplitudes have a pole structure that is quite simple. It's literally, there are simple poles. And these simple poles occur when intermediate momenta go on shell. The residue on these simple poles is a product of lower point amplitudes. And miraculously, or at least somewhat miraculously, the pole structure of bi-adjoint scalar theory and massive bi-adjoint scalar theory ensures that when you take the residue of the double copy on physical poles, you are guaranteed to get lower point amplitudes that can also be constructed by the double copy. So to reiterate, if I start with single copy amplitudes that factorize correctly on my physical poles, meaning just physical local single copy amplitudes, then this guarantees that if I construct a double copy from such amplitudes and look at the residue of that double copy amplitude on a physical pole, it'll factorize into lower point amplitudes, each of which can be constructed as a double copy. All right, so we don't have to worry about factorization. What we do need to worry about is what poles actually exist. And this is where we run into a problem. So you remember at 4 point that no new poles were generated and we were somewhat relieved. At 5 point, we ran out of luck, and the kernel does have non-physical singularities. In particular, the 5 point kernel, when you set all masses equal, so you have a single mass spectrum, looks like this. The denominator of the 5 point kernel looks like this, right? So it's a ghastly polynomial. Really, all we want to take away from this is that S12 equals minus m squared is not the only pole that this function has. There are non-physical poles as well. So it is interesting to see where this actually comes from, because we started off with physical amplitudes, right? So we had a matrix of physical amplitudes which couldn't possibly contain these bad poles. The problem arises when we took its inverse, right? So the inverse of a matrix is 1 over its determinant times a matrix of cofactors. The matrix of cofactors is also known by other names. I think it's called the co-adjoint, the adjunct, depending on where you grew up, where you did preschool. So again, the matrix of cofactors is just products and sums of elements of the original matrix. So that also cannot contain any spurious singularities. So the entire spurious bad pole content of the kernel comes from the numerator of the determinant of the matrix. And in the 5 point case, actually, this bad singularity structure is proportional to the determinant. So one other thing I would like to point out quickly is that this polynomial has an m to the 8th sitting out in front, which means that just like in the 4-point case at 5-point, we do not reduce to the massless double copy smoothly. Okay, so this feels like a bit of a roadblock, and we now need to salvage our formalism, and we need to make sure that the final double copy amplitudes are indeed local. And for this, we have two options. So the first option is that you kind of cross your fingers and you hope for the best. You go forward with the formalism the way it is, and you hope that there will be a cancellation between the spurious singularities in the kernel and the single copy amplitudes an. The second option is that you make sure by tuning the masses in your spectrum, you make sure that the KLT kernel has no spurious poles. And we will affect this by something called the minimal rank condition. So first things first, let's look at an example. That example will be massive Yang-Mills. And let's see how these two options play out in massive Yang-Mills. Okay, so what do I mean by massive Yang-Mills? So this is quite a naive extension of Yang-Mills. Literally, it is the Yang-Mills Lagrangian, and I've added a master. Right now, this breaks nice properties of Yang-Mills, and it's a slightly bizarre-looking theory. So you might wonder why one should choose this theory to study in the first place. And the reason we chose this to study was because of this map over here. So the Goldstone-Boson equivalence theorem basically tells you that in such a massive Yang-Mills theory, the longitudinal mode is going to look like scalars in a nonlinear sigma model in the decoupling limit. And as we know, the nonlinear sigma model is one of the special theories that enjoys being able to participate in the massless double copy. And its double copy is the special Galilean, which in itself arises in the decoupling limit of a particular theory of massive gravity. So I should say over here that this massive gravity that we are considering is DRGT, so Dirac, Gabardazzi, and Tolley, and it is a particular choice of the DRGT parameters that gives you the pure special Galilean theory in the decoupling limit. All right. So as a result, this might lead you to wonder whether massive Yang-Mills can be double copied of massive gravity. So let's look at option one. Option one says, fingers crossed and hope for a cancellation. So let's see how that works out. The 3-point amplitude is very simple. It's just a square of the massive Yang-Mills amplitude. And you get a massive graviton, a massive antisymmetric 2-form, and a scalar. The different external states can be projected out by replacing the polarization tensor by a projection operator for the different states. Already at 3-point, you have some nice features. You find that B parity is preserved, dilaton parity is violated. Moving on to 4-point, the form of the amplitude that's easiest on the eyes is this one over here, which is the color kinematic form, and the numerator is given over here. And as we predicted, it has no spurious poles and it factorizes correctly. In addition, it does match the well-known DRGT theory of ghost-free massive gravity. Pardon me. Good. So one thing to note here is that this massive Yang-Mills theory picks out a particular set of parameters in DRGT, and these set of parameters do not give you the decoupling limit that we wanted. So what this means is that in the decoupling limit, while we expected to find the special Galilean, what we find is the special Galilean with some extra coupling to the tensor mode. So long story short, this means that the massless limit and this version of the massive double copy do not commute. All right. Nevertheless, we move on to 5 point, where we had the problem of the spurious poles to begin with. And we find that there are no special cancellations between the massive Yang-Mills amplitudes and the determinant of the 5-point kernel, which means that massive Yang-Mills cannot be double copied to DRGT massive gravity by option 1 in D equals 4. So subsequently, there were papers by these authors over here, and this was actually first pointed out by our JHAP reviewer, that in D equals 3, the determinant of the 5-point kernel is actually proportionate to the gram determinant in 4 dimensions, which means that it reduces the rank from 6 to 5 in 3D. And this 5 cross 5 kernel still has spurious singularities. Somewhat miraculously, topologically massive Yang-Mills not only satisfies the BCJ relation you get because of this reduction in rank, but it also cancels all spurious singularities in the 5-point kernel to give you a local topologically massive gravity in 3 dimensions. So I would refer you to these papers by these authors to see the details of this calculation. Anyway, so to summarize, we looked at option 1. We looked at what happens when you try to naively double copy massive Yang-Mills, and you find that in D equals 4, there are no cancellations of these spurious poles, but in D equals 3, it is possible to do so. Okay. So let's now look at option 2, which is somewhat more interesting, I think. All right. So the idea of option 2 is to make sure your kernel has no spurious poles to begin with. We do this, and we conjecture that the way to make sure that your KLT kernel has no spurious singularities is to reduce its rank to n-3 factorial, which I'll remind you is the rank in the massless case. So we check this at 4 and 5 point, and I'll show you how it works. But before that, I want to add that when you do enforce minimal rank, you not only get a local double copy, you also reduce smoothly in the massless limit to the massless double copy, and you get BCJ relations. So it's no longer the case that any theory can be double copied. Great. Okay, so let's see what this actually means for theories. So at n equals 4, we have to reduce from rank 2 to rank 1 to achieve minimal rank, which means we just have to set the determinant of the matrix to 0. And this gives us the following condition on the squares of the masses in our spectrum. To remind you, the masses in red are the external masses, and the masses in blue are masses that are exchanged on each factorization channel. Right. And as I said before, you get a massive BCJ relation now due to this reduction in rank. And you'll notice that sending m to 0 just gives you the regular massless BCJ relation. At 5 point, you take the way to achieve minimal rank is to consider every 4-point subgraph in your 5-point amplitude and enforce that each 4-point subgraph satisfies this 4-point spectral condition. And that then gives you no spurious poles, a smooth massless limit, and massive BCJ relations. So this is all well and good. We now know how to get a local massive double copy. And that will happen when we satisfy the spectral condition. So what satisfies the spectral condition? Well, there's 2 ways of thinking about the double copy, either as a map between theories or as a map between amplitudes. In the latter case, you can consider special amplitudes that satisfy the spectral conditions. For example, Compton scattering amplitudes. And this has been studied before by other people, Compton scattering amplitudes and their double copies. And we find that Compton scattering passes our minimal rank test precisely because it satisfies the minimal rank condition. Somewhat more complicated case of satisfying the spectral condition is a theory that is a Kaluza-Klein reduction. So you're dimensionally reducing on a circle on S1, And as a result, your vertices are going to conserve KK number, which means they're going to conserve mass. So if you consider a process 1, 2 going to 3, 4, then your masses are going to satisfy these relations over here. And you can show that these relations imply the spectral condition. And the direction of that implication is important. Okay. So what you are to understand from this is that any BCJ compatible theory with a Kaluza-Klein tower of states and vertices that conserve KK number can be double copied. A partial arrow in the opposite direction was provided by Momeni, Rimbotis, and Tolley, where they showed that you can kind of go in the opposite direction. That color kinematic massive Yang-Mills is fixed to be a KK compactification of 5-dimensional Yang-Mills. So let me summarize what we've learned. We saw that by considering a massive bi-adjoint scalar theory, we can define a massive KLT kernel for a massive double copy. And amplitudes constructed via such a double copy will factorize correctly, but they might have spurious poles in them. Or rather, they will have spurious poles in them because the kernel has spurious poles in them at 5 points. So we need to path correct and figure out how to get rid of these spurious poles in the final double copy. And we have 2 options. The first is that the single copy amplitudes cancel the spurious poles. This doesn't occur in massive Yang-Mills in 4 dimensions, but does for topologically massive Yang-Mills in 3 dimensions, as was found by the authors that I can flash again. The benefit, though, the drawback of this type of cancellation is that it doesn't commute with the massless limit, and you may or may not have BCJ relations. The second option for a local double copy is the spectral condition, and this comes with the added benefit that it commutes with the massless limit and it has massive BCJ relation. And one of the types of spectra that satisfy the spectral condition is a KK tower, and so massive Yang-Mills with a KK tower indeed can be double copied. So I'll end with this slide of like where to go from here, and I think there's lots of interesting directions that one can go in. So one is are Kaluza-Klein reductions the only things that satisfy the spectral conditions? Or similarly, is topologically massive Yang-Mills in 3D the only thing that can cancel spurious singularities? So this kind of landscape exploration is important. But before that happens, I think we need to generalize this massive double copy formalism to include multiple masses running on intermediate momenta channels. And this is because we already know of a kernel that works in this way, and that is the string theory kernel. And so there's got to be something that interpolates, in a sense, between this formalism and the string theory kernel. Finally, there are other ranks that we can consider, not just n-3 factorial once you have fundamental matter, or you have amplitudes that don't necessarily satisfy the Kleist-Coif relations. So that's another direction. And finally, there is the question of supersymmetry. You'll notice that I didn't include n equals to 2 super Yang-Mills or some massive version of that. That is something that Laura Callum and I are thinking about now. And I'd be happy to discuss any of this with all of you. But thank you so much for listening, and thank you for the opportunity.
Thank you, Shruti. Let's all give a warm applause to Shruti for that nice talk. And we do have a couple of minutes for questions. Are there some questions? I see some hands raised, so I'll just call them in the order that I see them. The first one is from Mariana.
Hey, hi Shruti, thanks for the nice talk. I just have a simple question. So if I think of the double copy as a map between theories, it seems that in B equals 4, or maybe also in larger, the only option is for Kaluza-Klein theories to satisfy it. Is that right? Or do you expect that there's something more general?
So I guess there's two aspects to that, to the answer to that question. One is, so in this paper by Momeni, Rambutis, and Tolley, they show that it's true when you take massive Yang-Mills and you add effective operators, that the only thing you can get that is compatible with the VCJ relations is a compactification of Yang-Mills from 5D. Of course, there is the question of what happens when you're not looking at massive spin one. What if you have like a massive version of, I don't know, a massive scalar theory, like a massive version of the nonlinear sigma model or something like that. There is also a question of whether this is too simplistic. What happens when you're compactifying from not 5D, but from a different, a higher number of dimensions, not on an S1. So I think it's still an open question. Though there is some partial, as I said, some partial arrow in the opposite direction. But right now, the only proven implication is in this direction.
Okay, thank you.
Okay, Henrik, please, is next.
Yes. All right. Yeah. So thanks for a nice talk. I enjoyed it a lot. Yeah, I guess I had one comment related to the outlook that you had. So you discussed supersymmetric series. I mean, I guess one obvious case is when you have massive gravitinos, which is what we considered in some previous literature, in some previous papers, and in that case, yeah, it works. It works very nicely that you can get massive gravitino by double copying massive vectors times massive fermion, right? So that's a very natural thing to consider, and this is essentially you're breaking this supersymmetry spontaneously in flat space. So that has been considered. I guess there's also some early work on Kaluza-Klein that we had, which was essentially saying that spontaneous, like Yang-Mills on the Coulomb branch have the same partial amplitudes as Kaluza-Klein version of Yang-Mills. So if you can show that any one of those obeys polykinematics duality, it holds for the other one. And in fact, since we already know that higher dimensional Yang-Mills do obey polykinematics duality, at least at tree level. So I think there's no real doubt that it should hold for a generic Kaluza-Klein, at least at tree level, I guess. Yeah. But yeah, I mean, there's still many more things to explore, and we certainly did not explore all the things in our early work here. So,
yeah, I mean, absolutely. So both Compton scattering and KK towers, I think you've explored, and other people have explored. This kind of gives a retrospective understanding of maybe why those worked and other things didn't, I think. Yeah.
Thanks.
Okay, and if it's quick, we'll allow Lance a question.
Yeah, I guess it's quick. Thanks for the talk, Shruti. Yeah, I mean, I just wanted to explore the KK direction. I mean, I think you can go in more than one dimension, and then the mass relations will probably be more complicated than the ones you've shown here, and maybe people have done that. And then the next sort of more complicated thing would be, warped compactifications, where you have masses which kind of obey Bessel function relations, and there the overlaps or the couplings will change, I think, in a more non-trivial way. But has anybody looked at that second case in this context?
That's very interesting. I don't know of anyone who has,
Okay.
but people should feel free to correct me if I'm wrong, and there exists some work in that direction.
Thanks.
Okay, let's thank Shruti again for that nice talk.
Thank you.
And see if our next speaker, Yaroslav, is